And we decided something about energy, that we needed to add energy to this. Actually, as I do that. So we could add our energy term into this, and we said the energy term should show up where? Did we decide that?
Yep, on the right.
Show up on the right-hand side. That says energy. I'll fix that in a second here. Why did we say the energy should show up on the right-hand side? This is just pulling from what you already know. If you don't know anything, that's fine. Pulling from biology classes.
Because it reduces energy?
ATP is our storer of energy, and when we destroy ATP, we have to get that energy back out. Right? So it makes sense for energy to show up on our product side of this reaction. The last thing I ended with was then the sequence of questions that we've got at the bottom and trying to reference what these things are. So this is now going back to your backgrounds and trying to pull from what you remember of your general chemistry classes. If it was so long ago you don't remember those symbols, that's fine. We'll define them. Hopefully somebody does remember them. If you went from 130 into 230, check everybody's backgrounds on that. You probably won't even have any knowledge of what those two symbols are. So don't panic on that. Anybody actually know? Delta S? Delta S is our entropy, which we'll define here in a second. Delta H, our enthalpy. Has anybody heard the story on why they sound so similar? It's easy to get them confused, right? Enthalpy, entropy, as far as the terms. Literally, the guy that put together and figured out that entropy was an important factor, quite literally, realized that nobody was going to look at this extra term because it's kind of a small feature when we look at the global energy scheme, but wanted to make sure that people were aware of it and could think about it and would ultimately get it confused, named it in a similar fashion to enthalpy. Chose entropy as a name because it sounded similar to enthalpy. Nice guy. Yeah. And we'll see how those are related in a second here. We then have exothermic and exergonic, which are synonymous. Exergonic seems to be the biochem term. Exothermic seems to be the rest of the real world term. And then you get similar process with endothermic and endergonic, again synonymous. What are those referring to? Exo was what, sorry? Release of energy, I'm going to abbreviate with an E. Endo and ender refer to uses energy. That's actually the first time I've heard someone say uses. What do I usually think? You're right. Yeah, it's just the first term. Consume, I think, is usually what I hear before. A little more scientific on it. But uses is correct. Okay, consumes energy. These definitions for your exo and endo are fine per se, but we want to get a little bit more specific with them because we'll end up using them as their numerical values, or more importantly, the signs on their numerical values. If we look at an exothermic reaction, if I just give you an energy, how would you know it's an exothermic reaction by looking at that value? Has to be negative. Okay. And if it's endothermic, it's going to be positive, just the opposite. Okay. Catabolism or anabolism. And I swear at this point I'm really relying on you because I've never bothered to memorize that, and I know I've got the definition on the next slide because I never remember it. So catabolism is breaking down, so we're releasing energy, right? And anabolism would be consuming energy as far as our breakdown, it's going to be the opposite of that. It's building up. Okay. So we've just got a couple terms floating through here, and we need to be able to kind of interpret and see what's going on with that. So if we look at the equation, we now want to apply each of these concepts back to the equations to make sure that we understand when we look at a chemical equation which of those things is happening. So what do you see obviously first? Okay. Okay. I like your added emphasis in there. So we're looking at catabolism. Start to spell that right? Yeah. We're looking at a catabolism or catabolic reaction going left to right. In this case, we aren't concerned about the reverse. What clue within this equation would suggest that we don't want to worry about the reverse reaction? My reaction arrow is only going to the right. If we're seeing an equilibrium arrow, we have a right to left arrow, then we should worry about the reverse statement also possibly sliding in there. But as written, we're looking at catabolism, which then means what? It is breaking down, which we've already included in our catabolism definition, so let's shift to a different term. It would be releasing energy, which would be our exothermic or our exergonic. I'm just going to write exo. Okay, now we get to the harder ones. 2 more terms left. We need to be looking at our enthalpy and our entropy. And in particular, what we're going to be concerned about are the delta H's, and in particular, the sign. So when we wrote out what these things meant, we didn't actually specify anything about directionality with it. Okay, what would we expect of those signs? Now that we've got an equation to look at, we want to start to apply some signage to them. So if we look at our delta H, it's going to be very hard to come up with a number. I don't expect you to be able to calculate a number out of this, right? Because you would need tables and stuff. But I do expect you to be able to drop in a sign. Should it be positive? Should it be negative? Same idea for our entropy. Our delta S. We should be able to decide in this reaction, is it a positive entropy change or is it a negative entropy change? Any ideas? Okay, way to pick the harder one, but sure. Entropy was a measure of disorder is typically how it's classified. I like to think of entropy more as motion. The more motion, the more disorder, the more entropy. Okay? That also then gets rid of this negative aspect of disorder, and we're looking at a positive. Do we have more motion or less motion? Okay? So if we compare across the equation, which side would have more motion? Why the right side? There's more molecules. More molecules means there's going to be more possible things to happen, more motion. Which means we're starting at a low value, going to a high value. When we calculate a delta, the delta is always final minus initial. High minus low is going to be positive. So we have a net increase in our entropy or our motion. We would expect a positive delta S for this reaction.
All right, say that again. So you just said for knowing whether it's positive or negative. You said high to low, what was that? You expect?
So when we're looking at any of these delta terms, delta by definition is a change, okay. And your change is always measured by final minus initial. Right? That's every single delta you ever see, that's how it's calculated. Right? We would then go back to our reactions and try and decide something about the entropies. Okay? And in this case, all we really need are high and low. Which side of the equation has the higher entropy? The right side. So I'm taking a high numerical value and I'm going to subtract a low numerical value because my high is my final state.
Okay.
Make sense?
Yes.
What happens with our delta H? Our enthalpy. Did you say it's no good?
I said it's negative.
Okay, how do you know it's negative?
Because energy is being released. It's exothermic.
there's why I'm surprised you guys went straight to entropy. Thanks, Jimmy. The enthalpy is a little bit easier to interpret because the enthalpy is all about our energy release or consumption. Right? That's all delta H is really looking at. It is ultimately coming from our bond changes, and we would theoretically have to calculate it. Right? But in the grand scheme of things, we already mentioned that I think I mentioned that delta S is a very small contributor. So we then can correlate our release or consumption of energy pretty much directly to the delta H, in most cases. It's not always perfect, but it's pretty close. Which means if I have energy as a product, energy was released, it is exothermic, which meant a negative energy, which then means delta H has to be negative. Okay? Is that always necessarily going to be the case? No, we can definitely run into exceptions on that. And that's ultimately coming back to this term of our exothermic and endothermic. Those are looking at the overall energy of the entire system. Well, delta H is energy. Delta S, energy. They're both a form of energy. They contribute differing amounts to the overall term of energy. So we're missing another piece here. What is that other piece? Temperature is part of it. What's that?
G.
G. Gibbs free energy. Okay. In most situations, our delta S is so small that our Gibbs free energy is equal to delta H. So there's this new expression that needs to come in that brings in our Gibbs free energy that is the true kind of bearer of all of those extra terms. So if we erase all of that, what we now need to introduce is a new term, our Gibbs free energy, and ultimately our Gibbs free energy change, a delta G. That delta G is composed somehow of both our delta H and our delta S. What was that equation?
Delta G equals delta H minus T delta S.
Perfect. Okay. So if we took this back to the system we already had, delta H for this reaction we said was negative. Okay. Officially we'd have to go through and calculate it. Okay. Minus T. What sign would our T, or what is T? Temperature. What sign would our temperature be? I can have negative degrees Celsius. I can have negative degrees Fahrenheit. I can't have negative Kelvin. When we're looking at our Gibbs free energy, we have to be on the absolute temperature scale, which means our temperature will be in kelvins, which means our temperature will always be positive. Our delta S, in this case, was positive. Is it flickering? Yep, that's awesome. Which means our delta G in this case
No, negative.
if we have a negative number minus a positive number,
Never mind.
it'll be negative.
I was thinking multiplication.
It's okay. What if we have a stupidly huge temperature? Now the temperature, because it's a multiplier on our delta S, now our delta S term becomes incredibly important to our understanding of our delta G. So the delta S term could actually outweigh our delta H. Stupidly high temperatures. What's the sign on delta G? Still negative. We're taking a negative value minusing a stupidly high number. Still going to be a negative number. Okay, well, let's do the opposite then. Now the temperature is incredibly small. Let's just say it's absolute zero. Now the delta S term has no effect on our delta G, regardless of how big the delta S is. What's the sign on the delta G?
Still negative.
Still negative. So in this particular case, If I have a delta H that's negative and a delta S that's positive, my Gibbs free energy, the overall energy change for the reaction, will always be negative. Right? How do I determine the delta H and the delta S? The delta S, we can look at the reaction, look at the individual parts. The delta H is a little bit trickier. We would officially have to look at all the bonds breaking and all the bonds forming. And I know you love to do that calculation. We won't worry about it. Okay? I would tell you what your delta H is, be it positive or negative. Okay? I might throw in a little bit of a wrinkle. No, I won't. Never mind. Ignore that. Okay? Questions on that? Okay. If you've had me before, this figure should look really familiar because this is ultimately what chemistry is looking at. You're looking at a balance between kinetics and thermodynamics and how an individual reaction can work, how quickly it can work, if it should work, all of that fun stuff. So what we need to be able to do is to interpret for an individual equation where these different things or different bits of information are stashed. Okay? What we just talked about was all about energy, and in particular, the change in energy between our reactants and our products. That is our delta G shown at the bottom. This is one of the things that always irks me a lot when it comes to this, is that you will very often see, instead of delta G, you will see it written as delta H. Why might we write it as delta H? The delta S, first off, is relatively tiny. So for it to have an impact, we have to be at incredibly high temperatures. What class were we in? Not the room. What class is this? Biochemistry. We're looking at the study of living things, right? Okay. What temperature are living things at?
Most part, like body temperature.
Body temperature. Okay. We're looking at relatively low temperatures. If we have a relatively low temperature and a relatively tiny delta S, what happens to the term T delta S? Very small. It has a very small impact on the overall equation. So in most cases, we end up ignoring it. Okay? And our delta H becomes our delta G. Okay? Technically incorrect, okay? But it's one of those kind of approximations to simplify some of our calculations. Okay? That just tells us if the reaction can occur. That's our thermodynamics. Okay? But spontaneous combustion, the reaction, or let's change that around. What is spontaneous combustion? When you think of spontaneous combustion, what is it? Okay, an instantaneous fire explosion. So if we said one of you was spontaneously combusting right now, what would you expect to see?
Flames.
Flames. Guess what? We are all spontaneously combusting. Spontaneous, in the terms of chemistry, just means the reaction can happen. It is a favorable delta G. Okay. If we look at what happens when we burn organic material, say like wood, what happens? You see a massive release of heat. That's an exothermic reaction. Okay. We are organic material. If we burn, we will release heat. We are spontaneously combusting right now. We are converting complex sugar compounds into CO2 and water. Okay? That is an extremely favorable reaction. Okay? Why are we not all in flames?
It's happening microscopically in small levels.
No, because even in a burning wood, it's happening microscopically.
Or compartmentalized. I don't know.
It comes back to the figure. All we just addressed now is the thermodynamics. Does the reaction occur? Yes, it does. Spontaneous in the standard English language means something about speed. In chemistry, It just means it can occur. It has no speed effect. Why are we not seeing these big, massive flames?
Happens very slowly.
The rate of that reaction is very, very slow. Something is slowing that reaction or preventing it from occurring. All we've looked at so far is the difference between reactants and products. And we said that is massively exothermic, a big negative value there. What is preventing us from being engulfed in flames and even existing? Okay. The kinetics of the reaction, the activation barrier. There is an activation barrier that has to be overcome for us to spontaneously combust with the speed that we would expect with a spontaneous term used in everyday English. Kind of makes sense? So when we're looking at our reactions, it is a balance between our kinetics and our thermodynamics. Okay? We will be looking at both parts throughout the semester. Most situations, the kinetics will prevent a reaction from occurring. Okay? The odds that we can get ADP and ADP and a phosphate near enough to each other to form a product, to form ATP, is very, very limited. Okay? It's a disfavorable reaction. If we go ADP to ATP, we're adding energy into this, which means what's the difference between our reactants and our products? Our product energy is now up here, which according to our thermodynamics means endothermic, which also means reaction's not going to happen. Okay? Clearly the reaction does happen. How does the reaction happen?
It takes energy.
Okay? It takes energy, but I can take ADP and phosphate and put that into a container, and I can add tons of heat, and I will get some ATP, but my yield is going to be incredibly low. What else is added?
Catalyst.
Catalyst. Our enzymes, ATP synthase. Okay? We have to generate some system to help catalyze that reaction. And ultimately, that catalyst is doing what to our reaction? It will drop the activation energy. So even if I have a disfavorable reaction as far as endothermic, I can drop the activation energy enough that random thermal energy will give me enough to form my product. Okay? We can then deal with all sorts of other fun things like Chatelier's principle and all that, try and push our equilibrium further. Okay? Questions on that? Okay. Understanding something with our delta G's. Incredibly popular question when it comes to looking at any kind of standardized pre-health test, I've noticed. Okay, is looking at delta G's and delta H's and delta S's. Okay? They'll say given a delta H that is negative and a delta S that is negative, what does that mean about the spontaneity of the reaction? So what they're asking about with spontaneity is delta G. Okay? So we would go back up to our equation up here and say, okay, if I said delta H was negative and delta S was negative, is that what I said? Would I expect the reaction to be spontaneous? Well, spontaneous means delta G is negative. I got a bunch of negatives in my term. That probably means delta G is spontaneous. Okay? Is it? Not necessarily. There's the question that gets thrown at you on your standardized tests. Okay? Why not necessarily?
Because it depends on the temperature.
We have effectively a double negative in there. If the temperature is really, really large, what now happens to our delta S term?
It becomes large and negative.
Becomes large, and because of the negative in our equation, it's going to make it positive. So it's looking at the balance of how delta H and delta S interact with each other as far as their sizes go with respect to the temperature. Okay? This is typically put into a format as shown up here, and you can strictly just go through and memorize it and say this is how it works, and you're all happy with it. Okay? Or you can go through and go back to the equations and solve it each time by looking at the negatives and positives and saying what happens if I change temperature. Okay? I've noticed that at least when numbers get involved in it, students tend to get kind of bogged down in looking at the numbers. Okay? Make the numbers irrelevant. You make them irrelevant by looking at your temperature. You make the temperature 0, which means the delta S doesn't have an effect. I only have to look at the delta H. What does that mean about my temperature if it is 0? We're looking for broad general terms. So nothing, 0, not there, doesn't count.
Then delta H will tell you whether it
True, but what does that mean about temperature?
doesn't matter.
It's low. We're picking a numerical value for low. Low temperature is arbitrary. Okay? So we're picking an incredibly low temperature that we know then matches the definition of low, and we can then interpret out of our equation. What would we do for a high temperature?
1,000. I don't know.
Yeah, exactly right. 1,000, 50,000. Pick something incredibly large so that it will outweigh whatever the delta H is. Then you don't have to worry about the delta H. You're only looking at the minus your incredibly large value and whatever the sign is on the delta S. Okay? That then determines your delta G. That can help you go through and manipulate, and that's where you get the conditions shown in blue. Okay? I've shown them as two different colors because to me, if you're going to spend some time to memorize this kind of chart, memorize the blue. The red one, I think, is just kind of straightforward. If you see delta H is negative and delta H is positive, immediately jump them in as spontaneous or non-spontaneous as all temperatures. If you memorize this section, when you see negative, you've already memorized that delta S is negative. Now it's conditional. Okay. So by memorizing in blue, you kind of inadvertently memorize what's in red. Kind of makes sense? Okay. You for sure will see at least one question looking at manipulating your delta H's and delta S's to determine spontaneity for a reaction. Just to be more fun within that, this little diagram I feel is incredibly important to your understanding of chemistry, will also show up on the exam. Okay? That's kind of the end of chapter 1. Okay. So if we move into chapter 2, there's some kind of general stuff which in theory you guys have already heard multiple times. Every chapter or every textbook I've ever seen in biology, or for that matter chemistry, comes through a section and says water is awesome. Okay, every single one does it. Okay, well, why is water awesome? What does water look like? Oxygen with 2 hydrogens. Pulling way back, does this look like a valid Lewis structure? Yes. Is it helpful to our understanding of why water is awesome?
No,
Why not?
because how to describe it? I don't know how to describe it. Water's polar, and in this it wouldn't have any polarity.
Okay, how are you saying polarity?
How am I saying it?
How are you seeing it? Why are you saying this doesn't look polar? What about this?
Balance.
What's causing that polarity, though? I don't see anything in there to suggest we have some kind of
The electrons.
polarity to begin with it. Okay, what electrons?
Hydrogen electrons want to go hang out with the oxygen, so it makes those like.
The electrons here want to hang out with the oxygen. So you're right. You've added that extra layer of detail. Of course, now the next question will be,
Hydrogens are positive and the oxygen.
kind of, sort of. Because if you're going to make that statement, I'll throw in the counter argument. Which hydrogen is positive?
They're both.
Nope.
Don't they have polar ends?
This hydrogen, sorry, the purple structure of hydrogen. Which of those hydrogens is positive? Neither. So you can't tell me hydrogen is positive.
Only in water. That's what
Okay. Okay. I challenge that statement again. Is that hydrogen positive?
No.
Yeah.
Oh, it is?
Yeah.
I did not.
That is actually quite positive.
Yeah, because he wants to hang out again. It only
Why?
lasts one.
What's the, you're right. What is the why? Why is the hydrogen becoming positive? There it is. We're looking at electronegativity. The ability for any atom to attract bonding electrons. Do we have a bond here?
Yes.
Yes. Oxygen is more electronegative than hydrogen, meaning these electrons get sucked to the oxygen. If we push that to the extreme case, oxygen now has an extra electron that it stole from the hydrogen. If oxygen gains an electron, it becomes negative. Gaining an electron, sorry, and it may be back to the frame of reference, we're talking about our oxygen. If it gains that electron, it becomes negative. Well, what happened to the hydrogen on the other side? It lost an electron, it's now positive. Okay? Because we're still looking at a covalent bond, or a polar covalent bond, not ionic, we can't say that these are formally positive and negative. What we'd have to reference them as partial charges. Partial positive, partial negative. Okay? We could also see the dipole arrow. Sometimes you'll see that, where you've got the positive going towards the negative, if you will. That was an attempt to circle the line to represent the negative. Okay. What happens on the opposite side?
Same thing.
Same thing. And then this gets back to your point that you were making earlier as well. When we look at how this is now drawn, what happens to the dipoles of that molecule? They appear to cancel out. Okay. In actuality, they don't cancel out. They only appear to cancel out in our drawing. Why? Our drawing is two-dimensional. Okay. And how we've drawn it, we have not specified that three-dimensional characteristic within the molecule. So there's a couple ways that we could go through and do this. If we maintain the atom alignment, okay, so you are not allowed to now rotate the structure any different direction. The hydrogen must be immediately to the left of the oxygen. This hydrogen must be immediately to the right of the oxygen. How can I change that drawing to better represent that it has a dipole, that it is not a two-dimensional or a linear drawing? 45-degree angle means I'm moving one of those and it's no longer immediately to the right or left. We will get back to that because that's the easy way to do it.
Wedges.
Okay. We could then go through and say that these atoms are in front of the oxygen. Okay. Instead of writing in front of, that's a bit obnoxious, we want to come up with a symbol. The symbol we use is our wedge, to signify that those hydrogens are coming out of the plane at you. Okay. Did we have to use those? We could have just as easily have done dashes. In all of those cases, it's adding an extra layer of information, which is helpful, but it's also adding more work because we're having to draw more things. So what we are saying in this case is that the oxygen is the, what is that? The meat, the knuckle between my thumb and whatever that one is, index finger. The hydrogens are coming at you. What else could we have done?
Go down.
Rotate the molecule. Now all three atoms are in the exact same plane. If they're all in the exact same plane, do I need to show wedges and dashes?
No.
Nope. So I can now draw it. Where I can see a little bit more change in the structure, or a little bit more characteristics within it. And now, if we went through to look at our partial charges, do our charges directly cancel each other? No. There is a net dipole running towards the oxygen. Okay? Which means the oxygen carries a fairly large negative, and our hydrogen end of it carries a fairly large positive. It is this polarity that helps with water's ability to act as being an awesome molecule for all life. Okay. Why? Because it is polar, it can now react. It can also cause something else to react. By aligning that negative near another atom, that atom now starts to shift its electrons the other direction. Okay. We get a polarity within our molecules which causes other reactions to occur. That is one of the reasons why water is awesome. It is that large partial charge that comes from understanding something about how we put those structures together in their three-dimensional characteristics. Other parts of it that are awesome. Small size. Why would size be relevant? Go ahead. I think I heard what you said and I liked it. No? Okay. So I misheard, is that what you're saying? Okay, what I thought I heard was it can get through. See? I did hear it. And you're right. It can get through what?
Certain barriers.
Okay. Not even just certain barriers, nearly all barriers. If it was a very large molecule, how well would it be able to move around and get into different locations? Or even change its orientation so the negative and positive are aimed in different directions? A large molecule can't do that, which means it doesn't work well as a polar solvent to help everything out. The other thing that's nice, multiple symmetries. Okay? Meaning, I don't have just the negative at top, I have the negative all the way around up top. I have the hydrogens positive all the way around at bottom. There's a lot of different lines of symmetry within the molecule that, first off, give it that polarity, and then second off, give it the freedom to be able to interact in different arrangements. If it only had one possible arrangement, we've got a problem. Last part, we run into this hydrogen bond donor and hydrogen bond acceptor. What is a hydrogen bond?
Hydrogen bonding
Weak bond.
strong.
Hydrogen bond is weak.
It's bond to a strongly electronegative hydrogen.
A little disappointed in you, Jimmy. You're all wrong.
Nitrogen, oxygen.
Is there a hydrogen bond shown on this structure? Or in this image?
No.
No. How would I get a hydrogen bond shown here? I need another molecule. Is the hydrogen bond shown yet?
Not yet.
How do I get the hydrogen bond shown?
You have to the H of one molecule to the other one.
And I have to do a dashed line here, but it's supposed to be dots. Now I have a hydrogen bond. Here's the issue that I had with what you made, a lot of you suggested. You were suggesting that you had to have a hydrogen bound to oxygen, or nitrogen, or fluorine. Before I drew all that, did I have a hydrogen bound to oxygen, nitrogen, or fluorine?
Yep.
Yep, and yet, there was no hydrogen bond. Hydrogen bonding is not a strong bond or a weak bond. It's not a bond. It's a force. Okay. Bonds are by definition the sharing of electrons between two atoms. Hydrogen bonding is a force, not a bond, because we are not sharing electrons. Okay. We are looking at a weak attraction between opposite charges. Now that we know it's a force, is it a strong force or a weak force? It is a strong force because the partial charge from our oxygen is very, very, very negative. The partial charge from my hydrogen is very, very, very positive. Okay? So I'm trying to cancel those charges in that interaction. So I'm getting a very strong attraction between those atoms to try and neutralize that charge. Okay? Why is it so large?
Because of the electronegativity.
Half right.
Polarity.
It still comes back to electronegativity.
The difference in electronegativity.
The difference in electronegativity between the two atoms involved in the bond over here generate large charges. Oxygen is the second most electronegative element on the periodic table, followed by, sort of, nitrogen. What's more electronegative than oxygen? Fluorine. Our three most electronegative elements on the periodic table. Where's hydrogen in terms of its electronegativity?
On the other side.
It's on the other side, but that gets a little bit weird, because if we say hydrogen, there's plenty of other atoms that are more or less electronegative than hydrogen. Why do we not refer to a francium-oxygen bond potentially generating hydrogen bonding? There's one quick answer on that one. Why is the francium-oxygen bond incapable of forming hydrogen bonding? There's no hydrogen. That's our easy answer. We have to have hydrogen in a hydrogen bonding interaction. Okay? But that interaction between francium and oxygen in, say, another molecule is going to be even stronger than this one. So why am I looking at hydrogen bonding as the strongest force if there's another stronger force?
Those are bonds you're talking about.
When we look at the francium-oxygen interaction, okay, so one aspect, there's our francium-oxygen bond. If I now try to draw another molecule, put francium-oxygen over here, the interaction, I would get an interaction there that is not technically a bond. It is still a force.
Weak.
Is it weak?
I don't know.
The oxygen is second most electronegative. Francium is least electronegative. The difference in electronegativity between those atoms is massive. So massive that what happens? Oxygen becomes formally negative. The francium becomes formally positive. We end up with full charges here, which then means that interaction is better classified as anionic, and this is where it's fun. Anionic, what do we refer to it as? It's almost always referred to as an ionic bond, which is weird because we're not referring to a bond here, we're referring to the force, the attractive force between those. Well, what is the difference between this attractive force and that bond?
They're sharing and they're...
But they aren't sharing if I have a formal negative next to a formal positive? This is a formal positive next to a formal negative? What is the difference between those? Incredibly tiny.
But there is.
There is a arbitrary difference that we have put on that system. What is happening with hydrogen bonding? Hydrogen bonding is clearly a force. It is not a bond. Here we're looking at a force that could be confused for a bond because that force is now so strong it starts to become a bond. Okay? Hydrogen is the lowest electronegativity of the non-metals. Why is that important? Because that's how we get our covalent type bonds, where we're actually sharing electrons. It is different from our ionic bonds, because in ionic bonds, we straddle this weird gray area of not sharing electrons. Hydrogen bonding as a force is the strongest force that involves non-metals. There is no other element lower in electronegativity than hydrogen on our periodic table. Sort of. For most purposes, at least. Okay? So we end up with an incredibly strong force. This then moves back to the next aspect. Within that strong force, this hydrogen becomes partially positive, and it can share that hydrogen. So this molecule, or water, becomes a hydrogen bond donor, because it can donate the hydrogen into that interaction. It also is a very good hydrogen bond acceptor. Combine all of these elements or all these aspects of water in together as one big picture, and we end up with an incredibly useful molecule that can allow and facilitate lots of different reactions. Okay? It can even prevent other interactions because of these features. Okay? Questions on that? Put all together in one slide. This is probably my favorite slide and one of the reasons why I hate how forces and bonds are taught in classes. What's happening at a covalent bond?
Sure. Equally.
Sharing equally what? between what? Two atoms. So a covalent bond, I have two atoms that are equally sharing electrons. What happens as I move up to a polar covalent bond?
They're not equal anymore.
They're not equal. Okay. When do they stop becoming equal?
Never really ionic.
If it's never, then I should always have covalent bonds, non-polar covalent bonds, and never have polar covalent bonds. When do we stop becoming covalent and all of a sudden start becoming polar covalent?
The electronegativity of the two atoms is far enough apart. to-
What's far enough? I agree. Absolutely right. How many of you remembered or memorized that special number?
Hasn't it 0.05 or something?
Yeah, you cheat. Yes. Typically, it's defined as a difference in electronegativity of 0.5. If you are less than 0.5, you're classified as technically a non-polar covalent bond. Okay, so it's simple. Every time you look at a molecule, you look at the atoms and you just subtract their electronegativities. How many of you know the electronegativities for any of the atoms on the periodic table? Any atom. Any atom. I heard a 1.4, but I have no idea what that's to. So one of them is probably 1.4. Hydrogen is 2.1.
Carbon 2.5.
That's what I get. Okay, stop answering my questions, Jimmy. Anybody else? Because I'm pretty sure Jimmy's now going to run out of options.
That was bad.
Okay. So that is useful to tell us the difference between covalent and polar covalent, except you're not going to memorize your electronegativities. How else can you tell whether you have covalent or polar covalent bonds? We need an easier way to define those. Same element to the same element, which by definition will get you a difference of electronegativity of 0. Okay, so that very clearly fits in our covalent category or our nonpolar covalent category. The other one is carbon to hydrogen. Okay. So when you look at a molecule, you need to be able to say what type of bond it has, which will become relevant in the next section. Polar covalent. How do we know we have a polar covalent bond? That one's trickier. Well, difference in electronegativity greater than 0.5. But an ionic bond is also going to have a difference in electronegativity greater than 0.5. So how do we know we're between polar covalent and ionic?
Ionic was the difference of 1.5.
Depending on the number, yeah. So greater than 1.5 difference. But again, you come back to needing to know your electronegativities.
Non-metal with a non-metal.
Try that again.
Non-metal.
Metal to non-metal.
Oh, up there, yeah.
So what is polar covalent?
Non-metal to non-metal.
Everything else. Is that perfectly true? No, absolutely not. But it's darn close, and it will cover everything that you will see within this class, within biochemistry. Okay, why? Because biochemistry simplifies the periodic table just like organic chemistry did. Okay? So as we move from a covalent bond, we have two atoms equally sharing electrons. Eventually, we somehow become two atoms unequally sharing electrons. We then move up to an ionic bond where we have two atoms that aren't sharing electrons. What happens to become the ionic force? Where are forces defined? How did I define the force for hydrogen bonding? Where's my hydrogen bonding interaction?
The difference in electronegativity of the two atoms.
Had to reach a certain level, so we had to be a polar covalent compound. Where's my hydrogen bonding interaction right now?
It doesn't use that.
Doesn't there. I have to have a second molecule. I draw in that second molecule. Where's my hydrogen bonding interaction now?
Between the oxygen and the hydrogen.
Between what?
So it's your donor.
Yeah, you can get more specific. I want you to get more generic. We're looking at an interaction happening between
Two molecules.
two, take it even a step further, atoms. What was a bond? The exact same thing. When we're looking at bonds and forces, they are identical in concept, different in scale. A covalent bond is equal sharing of electrons. As I move up to an ionic bond, I'm no longer sharing electrons. I then at some point cross into this arbitrary threshold of now an ionic force, where those two atoms are charged, but now have some kind of strong interaction that I've decided isn't officially a bond, it's now a force. What happens as I move from an ionic bond to hydrogen bonding? What happens to that attractive force?
Goes down.
It gets smaller. Dipole-dipole. Smaller. London dispersion. Smaller still. Our relationship between bonds and forces is they are identical. It is one continuous spectrum all the way through it. And yet when you look at a rainbow, what color do you see? Way to answer too accurately. What colors are you told to memorize are in this? Roy G. Biv. But, as you said earlier, all the colors are present. Why aren't you told to memorize all of the colors possible? Because all of them are in the rainbow. It's too much. What's happening when we look at our interactions between any two atoms? It's too much to say they're all as one big thing. What we've done is arbitrarily cut lines and said at this point we are red, at this point we are orange, at this point we are yellow. Okay? Same thing is happening with our intermolecular forces and our bonds. Those then subcategorize into our different types of bonds and our different types of forces. So what we need to be able to do is to use that information to apply to larger molecules. How do we do that? I look at a structure that has carbon and hydrogen. That's going to generate a covalent bond. That is fixed. But now what I want to know is how does that molecule interact with others? Which means I now need to look at not the bond, but the force. What force is going to be generated by a covalent bond? A London dispersion force. By taking our continuous spectrum and pretty much cutting it in half, we can then overlay them. Covalent bonds generate London dispersion forces, which are weak. Polar covalent bonds generate dipole-dipole forces, which are stronger than our London dispersion. If we have a dipole-dipole force, we can then ask ourselves, do we have a hydrogen bound to nitrogen, oxygen, or fluorine? If the answer is yes to that, we haven't specified, but if the answer is yes, then we have hydrogen bonding, which is a stronger force than dipole-dipole. Okay. So what we need to keep in mind every time we look at these structures is how does this structure interact with something else? Why is this important? You heard of the lock and key description of enzyme reactions? Really? No? Nobody? Lock and key? Okay. Typically it's talked about in biology, they mention that one. Okay. Enzymes work by a key fitting into the enzyme that it can then do the reaction and it spits a different piece out. Why did the key fit in the lock? It's made for that. What about the lock makes it or allows it to fit? All of these forces. Okay. It's the application of those forces to individual structures that allows for all of biochemistry to work and function as we would expect. Massively important, massively undiscussed. Questions on what's there? Is that all review? So I shouldn't have talked about it? Is that what you're telling me? Phase transitions isn't as important for us, so we'll kind of ignore that. The solubility one is kind of important. How would we apply our solubility? There's a rule of thumb.
Like dissolves like.
Like dissolves like. What do we mean by that? Like forces dissolve like forces, which is polar. You're just getting more specific. Okay? So what we're trying to do is compare our overall polarities of those, or our forces of those molecules, and say, should they interact or not? Okay? Reactivity. You went through organic, you had Bronsted-Lowry, acids and bases. What is acids and bases an application of? It's the extreme case of hydrogen bonding now exchanging, instead of becoming a force, it now becomes a polar covalent bond. All of our reactions are how we change from our potential forces and transition into becoming bonds. Right? Every single one of them. So watch out for traps when you're looking particularly at solubility. You need to look at your bond type, okay? Then the force type. Then you also have to considerate the molecular considerate? Did I really just say that?
Good word.
It's good word.
Okay. The molecular shape. Okay. What do we mean? What type of bond would I have here? That's a carbon and not a uranium, a chlorine. Polar covalent, which would mean what type of force would I expect? Dipole-dipole. Would I expect this bond to potentially dissolve in water? What force does water have? Hydrogen bonding. This force has dipole-dipole. Those are kind of similar. Those are actually pretty similar in their forces. We might expect this to dissolve in water. Polar covalent bond, we've got a dipole here. That seems somewhat reasonable. What have I done here? All I've done is added more polar bonds. Well, if I have more polar bonds, shouldn't the molecule become more soluble in water? What do you mean not necessarily?
It's happy.
Well, we've got to avoid the happy statement. Third bullet. Evaluate the molecular shape.
It's harder for it to get in, to dissolve.
Not even get in. This chlorine is pulling the electrons this way. Where is this chlorine pulling the electrons?
Other direction.
The other way. Is there a dipole on that axis? No, there is no positive, there is no negative, because everything's happening opposite each other. How about on the other axis?
Same thing.
Same thing. Does this molecule have any polarity associated with it? No. This molecule ends up exhibiting London dispersion forces. So we have to evaluate the molecular shape on top of this. Okay. For those of you panicking saying that those aren't exactly on the same axis, you're right. That's where we'd have to evaluate VSEPR, which is valence shell, electron pair, repulsion, which gets us to our different shapes. You are ultimately responsible for understanding something about the shapes. If we have three-dimensional characteristics within our shapes, that's where we have our wedges and dashes. Okay. So there's a bunch of shapes. You'll notice that if you remember 151, 152, I didn't list a whole bunch of other shapes. Why not? In biochemistry, we don't care about them. We're going to stop pretty much at carbon bonding, so all we have to care about is our tetrahedral shapes. Okay. Notice that water is a tetrahedral shape that translates into a bent shape when we're looking at the molecule because we have lone pairs. Okay. Those lone pairs displace and hold space. Okay. This is kind of your overall shape summary. Okay. It is not a slide I had in there. After you and I briefly talked about wedges and dashes, I figured I should throw something up on this. I can get it to you later. Does anybody else want this summary slide for identifying shapes? Okay. I'll actually post it as an actual file so that you have that. It just summarizes all of those shapes. If you go to the tutoring center, they've got something similar that just has more stuff on it. So what can we do with these interactions? Why does salt dissolve in water? How come oil does not? Why does soap help oil dissolve? So we've got water. What does salt look like? into the abbreviation. Every point is a carbon. Carbon has to have 4 bonds. So some of those points only show 1 to 2 bonds, which means the other are hydrogens. Okay? So we've got our example of oil, and we have our example of salt. Why does salt dissolve in water, but oil does not?
Because it's polar, so we chloride is polar.
We have fairly large charges building up in each of these molecules. That positive can coordinate to that negative, forming a relatively strong interaction, which then allows for water to break apart the ionic bonds found in sodium chloride. If we go through and look at all the partial charges in oil, what are those partial charges?
There are no charges.
There are none.
There are no.
None. Absolutely none. Okay? Which means the oil has no real reason to interact with anything, period, even itself. If we now try and throw water in there, what is water doing immediately?
Trying to get away from.
Say that again, Jimmy? It's interacting with other water molecules. For us to dissolve oil, I have to break that water-water interaction to make a water-oil interaction. Which has the stronger attractive force? Water-water or water-oil? Water-water, which means
It doesn't interact with the oil.
doesn't interact with the oil. So by using our forces, we can start to separate and predict solubilities with these. Why does soap now all of a sudden help us to get oil to dissolve in water?
It breaks up the oil into small droplets. So
How?
Close surfactant, I don't know.
Okay, you're right. That is absolutely all true. Something about soap must interact with the oil. Okay, well, similar forces. Let's draw something for soap that's similar to oil. What would it look like? What would be similar to the drawing for oil?
Like oil, but smaller.
Okay, we'll go smaller. I'm fine with that. There we go. Now my soap interacts with the oil, but what do I have as a problem now? Does my soap interact with my water? No. So something about the soap must also interact with the water.
It's just a table or something.
It has to have something else on it. What's that something else need to be?
Functional group.
Right? Yep. Keep going.
A polar functional group.
There it is. This part is polar enough that it interacts with water. This part is nonpolar enough that it reacts with the oil. And what ends up happening, exactly as you described, your soap balls up around the oil, trapping the oil in with all of your nonpolar part of the soap, forming a ball where the outside of your soap is water soluble. And you end up with micelles. Okay. What happens if we scale that up even larger? Say like a liposome or a bilayer sheet. What have we just made?
Membrane.
Cell walls, membranes. Okay? All of that comes back to our intermolecular forces and how we can propagate those. Why would I need to incorporate some kind of nonpolar portion at all in my cell membrane? Why not just have it be polar all the way through?
It helps to regulate what goes in and what comes out.
If it was polar all the way out, our bulk environmental solvent is water. Which means if this was all polar, what does the water do to that entire polar cell wall?
Go right through it.
It goes right through. There is no cell wall. Our cells are now completely free-floating through a mass solution of water. Can we have a nucleus? Okay. We can't separate anything away from anything else. We just be one slimy mass of random pieces. There is no uniform life. Once we've got a cell wall where we can now separate and keep the outside world out, we can do that. What would happen if instead of water being our common solvent, we had oil? Oil is now the solvent of all life. What would we expect to happen? If we looked at our bilayer sheet, we still need some kind of cell wall.
The opposite.
If oil was somehow our creator of all life, we would have the exact same process happening, except it would be inverted. Right? Who knew you were in a reproduction class? Our cell walls would then flip because we're still trying to separate. We need that intermolecular force barrier preventing that interaction. Make sense? Kind of a neat process. Back to water. We said hydrogen bond donor and hydrogen bond acceptor. Okay. We can push water a little bit further and we can break it apart into H plus and OH minus. Okay. So we can dissociate back and forth. What does that end up getting us to? We end up with acids and bases, which gives us some form of reactivity. Acids, according to a horrible definition, but it kind of works, increases the H plus value while decreasing the OH minus. Bases do the opposite. They increase the OH minus value and decrease our H plus. Okay. If we go back to our equilibrium again, kind of a brief summary from 152. I know it was everybody's favorite. Okay. If we got an individual reaction, in equilibrium we have a forward reaction and a reverse reaction. That K represents the sort of, fair enough, I didn't point to the right K. The K sub F up in that top represents, it's the one everybody forgets.
Equilibrium constant in the forward direction?
So equilibrium constant was exactly what Mike said, right?
Right.
And that is not that K. Okay, you added an extra tier to it, the equilibrium constant in the forward direction. There is no equilibrium constant in the forward direction because equilibrium defines both directions. It is the rate constant. It helps us determine the speed of the forward reaction. K sub R is the reverse rate constant. How do we know we're looking at the rate constant and not the equilibrium constant? Lowercase k is rate, capital K is equilibrium. Don't shoot the messenger. Okay? If we go through and assume we reach equilibrium, equilibrium is defined as the rate of the forward equaling the rate of the reverse. We can set up some fun little expressions, rearrange those around, and we can group all of our like terms. We can group the rate of our rate constant for the forward over the rate constant for our reverse will equal to our products over our reactants. A constant divided by a constant is?
1.
Careful. The same value over the same value is 1. A constant over a constant is not necessarily 1. 2 is a constant. 1 is a constant. 2 over 1 is not 1.
Constant over a constant.
Is
Yeah,
just a constant. It's another constant. So instead of looking at it as two separate constants, we then define the relationship between those two constants as a new constant that we've decided to call capital K. That is now our equilibrium constant. Our equilibrium constant, we are now concerned about the relationship between our products over our reactants. Okay? This mitigates or removes all necessarily looking at rates, and we can just worry about our end result. Okay? And we can decide something then about our end result. To do that, we'll end up looking at pH, but we'll pick up there on whatever the next time is, Tuesday, because we're done. Okay? We'll pull through some definitions. It looks like this is going kind of slow for some of you, so I'm going to try and speed it up on Tuesday.